Okay, thank you all for joining. My name is Joop. I work at RevenueCat. Online, I usually go by J Shortway, which is the literal translation of my last name, in case you were wondering. Today I'll be talking about making native SDKs or single platform SDKs multi-platform and how we did that at RevenueCat, the approach we took, the struggles we faced, and we'll go a bit deeper as well with some more improvements we wanna make. So you might have seen our booth, but just to add some context about RevenueCat and the kinds of code we're working with, we are here to help apps make more money. That is our reason to be, basically. That's our mission. We do that by being a backend SDK, an SDK, so it's a backend and a mobile SDK actually, for subscriptions and in-app purchases. We have SDKs for Android, iOS, Flutter, React Native, Unity, even more. And our latest addition is Kotlin Multiplatform. It's been out for about a year now, but it's the last one we added. The V1 is out for a year. Yeah, so we aim to be easier to integrate than Apple StoreKit and Google's Play billing library. These underlying technologies, we still depend on them, but you don't have to. They change over time, especially Google Play's billing library changes every year. They make you update. You can at most delay the update by a year, and then your app update won't be approved anymore. So you need to stay up to date. We try to do that for you. We smooth that over. On top of that, we have a backend as a service, as I mentioned. We have a ton of features that this backend unlocks. A non-exhaustive list is that we do receipt validation. So we make sure that their purchase is actually valid. By default, we support cross-platform entitlements, which means if a user subscribes on Android, they're automatically also subscribed on iOS and vice versa. You can, of course, configure this differently, but this is the default. You can build this yourself, but you have to have your own backend for this, and so this is one of the features we provide by being this service. We normalize all the purchase data. Every store formats the purchase data slightly differently. We normalize all of that for you and make that available in an easy-to-use dashboard. We have charts. We can analyze it all the way you want. We have a ton of growth tools as well to help your app grow. One of those is price experiments. So you can actually run A/B tests with pricing to see which price works best for your business model. Another feature we have is paywalls. This is a nice collaboration between the backend and the SDK, or actually the website. We have a no-code paywall builder in the editor on our website. It's a Figma-like interface that allows you to build a paywall, and that then gets rendered by the SDK as server-driven Jetpack Compose in the case of Android, SwiftUI in the case of iOS. This is really useful. You can update your paywall without having to update your app. You can change the paywall for Black Friday, for instance. It's super convenient. You can test different paywall designs, all without having to ship updates for your app. Another feature that is a collaboration between our servers and our SDK is Customer Center. This is also a sort of server-driven UI. Technically it is. It's a page that you can add to your app, which allows users to manage their subscription. And this aims to cut down on support requests. You can configure the options that show on this page, but things that you can choose to show are requesting refunds or canceling subscriptions. And so giving the users the tools to do that themselves so they don't have to contact support for this. You can even configure it in such a way that if a user tries to cancel, you can show them a promotional offer, for instance, with a discount or something like that, if you want to do that. So that's a little bit about RevenueCat. It's more for background context. It's not really what this talk is about. Because this talk is about how we built the RevenueCat SDK for Kotlin Multiplatform. We can generalize this a little bit more and just make this a general problem that we face. That is, you have existing single platform SDKs. You have for Android, you have for iOS. You want to have a Kotlin Multiplatform SDK. More generally, you want to support Kotlin Multiplatform apps from using your SDK. Of course, Kotlin Multiplatform is super flexible, so like in the worst case scenario where you don't have a Kotlin Multiplatform SDK, users can just depend on your single platform SDKs in the source sets. But that's not you don't want to force your users into doing that. It's nice if you ship that Kotlin Multiplatform compatible API layer. So the solution to do that, of course, is to just rewrite everything in Kotlin. That's how you do it. Thank you, and see ya. No, hold. Of course, that's not the real solution. The real solution is to adapt your single platform SDKs for KMP. And how did we do that? What is our approach? Just to reiterate on this point, or yeah, just to share this example. In an existing project, or let's say in an app project, it's common if you start to introduce KMP that you go bottom up. You might start with a networking layer, the persistence layer, because often if you have, let's say you have an Android and iOS app, they might be talking to the same backend API if they're just client apps for your backend. They might have the same caching or persistence logic. You just wrote that once in Swift and once in Kotlin, for instance. You might have different teams doing that, but in general, they're implementing the same spec. So if you would introduce KMP in such a project, it's common to start by rewriting let's say the backend API into Kotlin and then being able to share that with iOS. However, that's not our primary goal in this project. We weren't looking for the efficiency gains. While they're really nice, that was not our goal. We want to be compatible with KMP, basically, for KMP apps to consume us easily to consume our SDKs. And because our primary goal is different, we weren't looking to share code, but we were just trying to be compatible with KMP. We went the other way around. We went top down. That meant that we created a new KMP library, started as an empty library, of course, and then we made that depend on the Android and iOS single platform SDKs. So KMP is just the unified API layer on top. There's no logic written in KMP. The reason why we didn't want to rewrite stuff, though the main reason, is because we have battle-tested SDKs and we are critical infrastructure for our implementing apps. We handle payments, we handle monetization. We absolutely did not want to risk not covering the same ground by rewriting, let's say, our Swift logic into Kotlin. So that's why we went this way. Then we also initially used type aliases for minimal runtime overhead. This seemed like a great idea at first. It is also still, I think, a great idea. But eventually we discarded this before we shipped our V1. And the reason why we did that this is how we did it at first. We declared an expect class in our common source set. Then instead of providing an actual class in the platform source sets, we provided an actual type alias. And we would type alias to the type from the native SDK, from the single platform SDK. This worked great. And the absolute best pro in this case is that there's no runtime overhead. What that means is that at runtime, the implementing app, when it speaks to RevenueCat, it's directly talking to the Android SDK, for instance, in the Android build scenario. And on iOS, the situation is very similar. So the KMP layer basically vanishes at runtime. That is, of course, a great pro. However, there's one con which caused us to abandon this idea, and that is because we're type aliases, we're not shielding the platform API in the platform source sets. They're still available to consuming apps. What that means is the following. Let's say in common main, you can import only our KMP classes. So this is just an example model class we have, customer info. It's the KMP version of that. However, in Android main, both the KMP version and the Android version, the one that ships in the Android SDK, both are available. So we cannot guarantee that users aren't actually or accidentally using these Android types. This is firstly confusing for users, and second of all, it makes it so that we cannot change our mind about this without making a breaking change. If we want to do things differently, which would cause the Android types to no longer be available, we would have to make this a major semantic version update, because people might be using this and it would be a breaking change to just remove those types. So for that reason, we went with wrapper classes and mostly just mapped the common type into the platform type in the platform source sets back and forth. It's not as nice in terms of runtime overhead, but we completely shield off the platform API. And so the only API available to consuming apps comes from our KMP layer, basically. And this gives us the room to change our mind about how we actually implement this, how we architect the SDK. This works fine. It works well. People are using this in production. It's all great. It's been out for a year. However, there's unfortunately, or as usual, I guess, room for improvement. My biggest gripe with our current setup is the following section in our documentation. We have this part in the integration docs. It says you have to link the native iOS SDK. Since the SDK depends on a native RevenueCat iOS framework called Purchase Hybrid Common, this will need to be linked to your existing iOS project. What this means is that users will, depending on which package manager they're using, either Swift Package Manager or CocoaPods, or maybe even others, but those are the main ones we currently support. They will need to, in addition to declaring our KMP library, they will also need to declare a dependency on our iOS SDK, the Purchase Hybrid Common one. If they use Swift Package Manager, they need to do it in Xcode, or they can use it and do it in Xcode. If they use CocoaPods, they need to manage a pod file. This is all a lot of overhead in addition to just putting the dependency in the Gradle file, which is the common way of doing this in the Kotlin world. This is because KMP libraries, they are published to Maven. Android libraries are published to Maven as well, so this is great. However, iOS libraries, they're not published to Maven. They're published to Swift Package Manager, CocoaPods, or even other package managers. There's a bunch on iOS. Swift Package Manager, definitely the most popular one. So what this means that we have the following problem. KMP libraries cannot automatically resolve transitive iOS dependencies. That just doesn't happen. So that's why we have this extra step for users to do manually. In our case, this means that developers need to manage two dependencies, as I said, which is a hassle. I'd rather not put our consuming developers through. And our version numbers look like this. We're basically shipping two dependencies. They have two versions. This is actually a valid semantic version. The plus allows you to add a build metadata field, which is freeform. We use it to add another version, which is the version of our Purchase Hybrid Common. If we update our SDK, users will have to update this version string, but also need to be mindful of the fact that if that second part has updated, you need to also go into either Swift Package Manager or their pod file and update that specific version there as well. This is not great. I don't like this developer experience very much, but it's the current world we live in. So how do you actually add transitive iOS dependencies to a KMP library? Or how could you do it? This is just one way. There's at least one other way that I am aware of, but this is currently the way we are exploring and that I'm writing a proof of concept for or on. The short answer to all of the following slides is you just embed it as a static library. However, the longer answer to that, so if you embed it as a static library, the iOS dependency binary just gets completely included in your KMP library. There's no transitive dependency anymore because the library is just there, basically as a file. It gets linked, it gets hooked up properly. That works. Long answer to how to do this is you need to create a Syntrop definition file Sinterop is the Kotlin Multiplatform feature or Kotlin native feature actually, that allows you to interop with other native languages, in our case, Objective-C. In this location, this is the default location, the native interop folder /Sinterop. You give it a name, we named it RevenueCat. And it should contain something like this. In our case, it contains something very similar to this. You define the package. So this is just your Kotlin package, Java package, where your code ends up, or your bindings end up, actually. You define the language, you name your module, and then you define the static library that you want to include. In our case, lib_revenuecat.a. An A extension is the static library extension. You define where to find this static library, and then some compiler and linker options. The compiler option is the most interesting one. You specify where you can find the headers to the lib_revenuecat.a static library. If you do all that, then you need to add it to your build file with a section that looks a bit like this. So you configure the main compilation of your native target. You add a Sinterop's configuration block where you specify the name of your Sinterop file. And then, of course, we have the problem, like I mentioned, we need to provide this lib_revenuecat.a file, this static library file. How do we get that? We, as part of publishing our iOS SDK, we don't build this file. It's not needed for anything. We build a framework file, and also we publish on CocoaPods and on SPM. And those are actually just references to our source code. That works slightly differently from what you might know in Android, where you publish compiled bytecode. So as of now, we are not producing this file anywhere. So how do we do that? You could manually, or in a Gradle task, run a Swift build command in your iOS dependency source folder. This will compile your iOS code and turn it into this static library. You can do this as part of your build in, as I said, a Gradle task. This is more flexible for local development. Local development of the iOS dependency is what I'm referring to here. So if you change that a lot, then this is useful because you will always compile the latest version of your iOS SDK when you compile your KMP SDK. And of course, this means that you need to add the iOS source code to your build. And one way to do that is to use the Git submodule. So if you have two repos, one for your KMP library, one for your iOS library, you can add the iOS repo to your KMP repo as a submodule. That's not the focus of this talk, but that's how you could do it. You can also build this on CI if you want. It's a lot less flexible for local development, but if your iOS dependency doesn't change a lot, then that's totally valid, of course. If that file is just pretty much static, then you can do that. Yeah, so it can be feasible if you don't need to do much local development on your iOS dependency. But the easy mode to do this is to use a different plugin called Swift Klib. You can find it on GitHub here. It's made by someone else. It's really great. It makes this a lot easier. All you have to do is you add the Sinterop definition as before to your build. So this is the same statement. You configure your main compilation of your native target. And then you configure Swift Klib. And Swift Klib has its own, it's a Gradle plugin. And so it has its own extension where you can configure it. You specify the path to your source, your iOS source, which you can see is defined here. You specify the package name as before, and you can specify stuff like minimum iOS version. In this case, it's read from a version catalog, like that. And then it just works. Like it compiles your iOS code, and it's added as a static library to your build. So that part is great, and it's very straightforward to do with Swift Klib. When you publish a Kotlin Multiplatform library, it actually publishes a bunch of libraries, like different libraries for every target. If you publish an Android target, it's an AAR file, just like an Android library would be. If you have a native target, it's published as a Klib file. That's Kotlin's publication format. Klib file is just a zip file. And so if you unzip it, you can see that in the included folder, we now have our static library included. So yeah, that part, it all works great. It's not very difficult to do this, especially with the Swift Klib plugin. But we're not there yet. Let me take a sip of water. We have some speed bumps on the road, unfortunately. Number one is that we actually have two iOS libraries, not just one, and they depend on each other. We have our core library called RevenueCat, and then we have our UI library called RevenueCat UI. And this UI library contains the paywall stuff and the customer center stuff, and that one depends on the core RevenueCat library for all the core logic, like the talking to our backend stuff, the purchasing logic, all of that. And Swift Klib actually generates a package.swift manifest file, but it doesn't declare any dependencies. Like, it doesn't support any way of declaring dependencies between different modules. And it breaks the build because our RevenueCat UI Swift code imports the RevenueCat module all over the place, and it will fail compiling because it says, I cannot find this RevenueCat module. I don't know what you're talking about. So the solution to that is to adjust Swift Klib's package.swift generation logic and add support for declaring these dependencies. This is such a package.swift file. If you haven't seen it before, this is something that Swift Package Manager uses. And this defines a RevenueCat UI module. The parts we're interested in are the two dependencies parts. The first one is where we specify where to find the RevenueCat module, like the path to it. I think this also supports like Git repositories and stuff, but for us we have it locally because we added it as a submodule. And then below that we have our RevenueCat UI target, and we say that that target depends on the RevenueCat dependency that we specified before. However, this file is generated by Swift Klib. Like, we don't actually write this manually, so we need to make sure that these contents actually end up in the file. This is the function that generates this file. It's just a string template, so it's very straightforward. We can add some not very pretty looking, but serving the purpose of proving the concept code here in these locations, and this will make sure that if we provide a dependency, then the line gets added, basically. Again, this is I wouldn't actually commit this, but it's functional. A second speed bump is that one of our iOS libraries, the UI one, has resources. It has some strings, it has some icons, it also has some images. That makes Swift require us to declare default localization. Swift complains if we don't provide that, or if we don't declare it, that manifest property isn't found, and we need to do that in the presence of localized resources. In our case, our strings are the localized resources. And we also need to declare these resources, actually. We need to say where they are. So the solution, again, is to adjust the package.swift generation logic. Again, this is the Swift package.swift file. This is the default localization line that we need to make sure that is added. In our case, the default localization is English. And then we need to specify the resources. You can see that we have the background.jpg file, an icons pack, and we also have strings. They're not defined here. Again, this is the string template function. I'm not proud of this code, again, but this is just a way to make this, prove this concept. You can add the default localization line like this. Just if it's not null, you write the string there, and then the dependencies are added here, or defined here with the resources function that I wrote. And this is horrible. It just adds that whole string block there if it finds that the syndrome name is the one we're looking for. This is very static. We will never use this, but I just needed to make sure that the package.swift file was correct. And this does that. So now we have declared our resources. We can compile both modules. They know that they depend on each other, and they know where to find resources. Compiler is happy. Unfortunately, the resources are not actually included in the static library. So if we now build our KMP library, the resources aren't there. So it thinks it can find the resources, but they're just not there. The bytes are not in the klib, or not, yeah, they're not shipped. There are some things that you might think are a solution to this, but that actually are not. The first one is to use composed multi-platform resources or MoCo resources. These are tools that allow you to use resources in the Kotlin native world, but they don't work for our case because they're geared towards shipping resources in apps and not in libraries. And why that matters is because they are a Gradle plugin, and we're not a Gradle plugin, and we're just a dependency. And they are a Gradle plugin because they will copy the resources from wherever they're defined into the final framework that gets built from your Kotlin native code when it's built for iOS. And we are not at that step. That's a step ahead of us. Like that happens after we are done with just shipping our library to Maven and other package managers. So yeah, we're not present there. We could decide to become a Gradle plugin. But like philosophically, I'm not sure if that's the best way forward. If every KMP dependency that needs to ship resources on iOS is going to become a Gradle plugin, then people will be declaring their dependencies in the plugins block instead of in the dependencies block, which is not what the plugins block is intended for. Also, all these plugins will effectively be doing the same thing. They will be copying resources into a framework. So I'm not sure if that's the direction to go. Another thing that is actually not a solution, but seemed promising at first, is that, as I mentioned, klib file, just a zip file. So, and it even has a resources directory. You can see it here, like this is the default contents, the structure of a klib file. Resources folder is there. So I figured like there's a resources folder, we must be able to use that for resources. I manually put the resources there. I didn't write a Gradle task for it. I just put them there, and I published to Maven local, and they stick around. They are still in the resources folder after you unzip the published klib file. You can see our string files, the lproj folders are the strings. We have the background image. They're all there. Unfortunately, when you actually build an app that depends on such a KMP library with resources in the klib, the resources are not like actually shipped into the iOS app. So that means that our iOS SDK at runtime cannot find these resources. There's one thing that is a potential solution, and that's the following. We could declare the resources in code. It's definitely not pretty, but it's doable. I actually found this in the Kotlin Lang Slack. Someone named Matt Nelson figured this out in 2023, or had the same problem as I did in 2023. And they say, in their case, they were actually concerned with shipping executables into their Kotlin native. So they would compile them, code sign, or notarize the Darwin targets, and then the third point is the most interesting one. They wrote a Gradle task that reads and writes these resources as base64 chunks into a Kotlin file. And then in their case, at runtime, they wrote it to a specific directory. For the sake of proving this concept, we don't need to do that. We can just read it directly from the Kotlin file. They called it insanity, but doable. I tend to agree with that. So they actually created a tool for this on GitHub called Resource CLI, a CLI tool that allows you give it resources and you get back Kotlin files that just state these resources as base64 strings. So I used that for a one-off test. I gave it my resources. I get files back that look like this. So this is in a Kotlin object called resource localizable strings. It implements native resource, or it extends a native resource class. It has some properties. It has a checksum, for instance. It has a name. The most interesting stuff is that it has a get function that just takes an index and returns a chunk. And it has a bunch of chunks. In our case, just one, just the chunk 0, because this is a very small resource, but you could have multiple chunks if your resource is very big. If your single file is very big, you would have more chunks here. This is the base64 string. I took out a lot of characters in the middle, but you get the idea of that this is the actual resource file, the base64 representation of the resource file. Now, our underlying iOS SDK, of course, needs to read these resources, because they're not where the iOS code expects it to be. We can do that as follows. We can declare a protocol in Swift, looking something like this. Objective-C headers, of course, for the interop. I just call it resource provider, and we need, in our case, we need strings and images. So I added these two functions. We can provide strings based on the locale, and we can provide an image based on the URL for an image, which in this case is a local URL because we're talking about local resources. We can then implement this protocol in Kotlin, of course. Just, again, a very quick implementation of this is that you check the locale identifier that you get and then pick the right file, and then use a very unoptimized way to read the chunks into a byte array, and then, in our case, split this. This is just a big string that you get, and you need to split it in a certain way to get a map out of it. It's keys and values. If you're used to Android, it also has strings and keys and values. That works like that as well in iOS. And this is very unoptimized, but again, works for the POC case. The image data, you could do something like this, where you extract a name from the URL, and then if you match the name to something, you read the bytes from the base64, and because Swift, or iOS in general, will expect data or NS data, you will have to turn your byte array into NS data, and you can do that with the last line here, where NS data dot data with bytes line. Of course, this when function, where you just check the name literally to background of JPEG, and then previously where you check the locale identifiers to literal values, these are prime targets to be generated. You don't want to write this code manually. You just want to have a generator look at the resources you have and then just write this when statement for you and the rest of the function as well, of course. So, are we there yet if we do this? Actually, we are. Here's our paywall. This is our fallback paywall. We show this if there's a configuration error, and this is actually the main thing that uses local resources, because we want to be able to show this paywall if something goes wrong. So we cannot rely on the network for this. This is a way to remain functional even in case of errors. Of course, as we are critical infrastructure, we want to remain functional at all times. So users need to still be able to purchase something, even if there was an error in the configuration. For instance, maybe a translation was not provided or something else went wrong. This just shows all the products. The continue string, the restore purchases string at the bottom, those are resources. The background is actually the background.jpg file, but it's blurred. So that's also resources. These are all showing correctly now. So after we went through all of this, it does work. So that's good news. But of course, this is not super straightforward. There are definitely downsides to this approach. This becomes very unwieldy if your dependency graph is very large. In our case, we just have one dependency, which is our own iOS dependency that we want to do this with. In general, if you're a library, it's a good idea to minimize your dependencies, and that really helps in this case as well, if you're already following that advice. Also, developers cannot depend on your transitive dependencies separately. So if you are including statically a dependency that is maybe not yours, but very popular, and people might be using that next to your KMP SDK already, bad things will happen. They might be using different versions. You are also like statically providing this. There will be conflicts. So this is troublesome. In our case, it's fine because people will not be using the iOS, or the chance of people using our iOS SDK next to our KMP SDK in tandem, I think is very low. And we can support that use case from our KMP SDK already. Like they can call through to the KMP code from Swift, for instance, if they need to do purchases from Swift. So in our case, it's not a problem, but it could be a problem if your situation is different. Also, you need to somehow have access to the static library or the code archive, the .a file. It's a code archive static library for each of your dependencies. Usually that's not a problem. Most dependencies are open source, but if they're not, then that might be an issue where maybe the dependency does not provide you with a static framework, static library, sorry. And specific downsides for the resources like solution. You can stream the resources, like you don't have to put the entire resource in your memory because they're split up in chunks. But you have to decide the buffer size at build time. Like you have to decide how big the chunk is going to be because you define that chunk at build time, basically. In our case, that's totally fine because we have minimal resources. We have a few strings, a few icons, one image. So the resources are not very big. But if you have very big resources, then you might need to take this into consideration. Might especially be problematic if you run on like constrained runtimes where you have limited memory. You need to really think about this. Also, another downside, of course, is that the iOS platform code or iOS dependency needs to adapt to this. It cannot use the standard iOS resource APIs, which would be getting the resources usually from the bundle on iOS. It will need to call into the Kotlin implementation that we wrote, which is our resource provider. So suddenly our iOS dependency is now aware of the fact that it runs in like this Kotlin Multiplatform or Kotlin native shell, which is not ideal, but it's the downside that we have to worry about and we have to deal with, which I think is a lot better than having a downside that the users need to deal with, or in this case, the consuming developers of our SDK. As I mentioned, there's an alternative to this whole approach. The alternative is to be a Gradle plugin. In this way, you can wire your dependencies and your resources effectively because you're part of the build. You're at the build step where the final app gets built. Sentry actually does this. They have a Kotlin Multiplatform library as well, and theirs is open source, so you can check that out if you're interested in that approach. Their booth is actually opposite to ours, so if you're visiting ours, you can visit them and you can ask questions to both of us. So, of course, as I was alluding to, the code I showed was terrible, so there are a bunch of next steps that we need to do to actually start to implement this. One is that we want to generate the resource files as part of the build. I just ran them through the CLI once, but that's not scalable, of course. The resources might change. You need to manually run them again. So ideally, this is just a Gradle task that runs as part of your build that generates these Kotlin files containing the base64 chunks. They can also be, I haven't tested, but like they can also probably be just byte arrays that you literally declare. And then the resource consuming code, as I also said, like these when statements that check the locale identifier or the image name. You want to generate those as well, because at build time you know exactly which resources you have, which locales you support, so you can generate these when statements and all the consuming code. Because yeah, it's very error prone if you need to do that manually. Some closing words. Our repo is open source, so you can check it out. All of the mobile SDKs are open source, so as I said, the KMP SDK depends on iOS and Android. Those repos are open source as well. Feel free to open issues or ask questions or make noise in the repo, whatever you want to do. You can check out RevenueCat.com if you're interested in monetizing your app or your app through subscriptions or in-app purchases, or just want to see what happens. As long as you make less than $2,500 a month, it's totally free. If you make more than that, it's just 1% of revenue is the cost of RevenueCat. Come by our booth, say hi. We're like opposite Sentry, and we're in the same space as Google, basically. We're on the other side of Google's booth. We're hiring. We have a bunch of open roles for Android, iOS, and other engineering roles. So if you're interested, also feel free to check that out. That was it for me. Thank you. Don't forget to vote. And thanks for your time.